So my point is, learn it right now so you struggle less later in Calculus 3. And it has lots of applications anyways. Those are my steps. You don't have to follow them. But when you're stuck with the problems like this, it's nice to know steps. You follow them, it works. Last time we covered the theorem called Fermat theorem that says if you have continuous function on the closed interval, it must have min and max. So the function can be crazy, wiggling, whatever you want. But if it doesn't have breaks, jumps, gaps, or holes, and it has a closed interval, it has global max and it has global min. There's no way it disappears and reappears somewhere, so now you cannot recognize where the min or max is. There's no vertical asymptote either. So if it has a vertical asymptote going down or up, the function's decreasing or increasing, there will be no max and min, absolute one. But in this case, it is the case. The easiest example is your age. Your age from year 0 to year right now, whatever you are old, 19 years old probably, I guess. So there's definitely min and max. There's no way you suddenly skipped and now you're 35. At least the technology did not go there that far yet. So let's find it. Let's work on the examples right away. Here's the example. Find the absolute mean and max points. Points will mean a pair. That's why I put it in bold. A pair means x, y. That's important because you usually find x and then you forget to put y, and we usually require you. Here's the function. X to the 2/3 times 2 minus x. Let's find absolute mean and max. If it's not restricted on the interval, this interval is your domain. And if you watch Jujutsu Kaisen, we don't do domain extension in this class. But if there's no domain restriction, then there is no absolute max and min. The functions keep decreasing forever and increasing forever. On the left, right. But the moment we cut it off, now we can find max and min. Let's see. Do you see local minimum? Last time we covered definition of local minimum. It means minimum locally. Exactly what it means. Or in the neighborhood. Neighborhood is a mathematical terminology. Plus minus epsilon, if you know what it is, or basically plus or minus small step size. This looks like local mean. So I graphed this function for you. You guys are talking, I can hear you. Thank you. Whoever's talking always distracts me, mostly because my translator from English to my language keeps running and I cannot stop it. So I have to translate you, myself, and everyone else. Too destructive. So that is local minimum over here. Then this guy is global max, just from the picture, right? And this guy is global mean, just from the picture. So if I ask you to find visually, this is how you go. There's also one more local max, this little hill. Local max. So we have local mean, local max, because locally over here, it's a hill. Locally over here, it's a pit. But the thing is, what I just did is not what they asked me to do. So this is visually, we give this problem for the not math majors. We give it on the picture and can you kids find out where the biggest point is? And they're supposed to write down minus 310. And that's maximum points for you. For STEM people, we actually use derivatives to define it. Whatever I did happened from minus 3 to 3. Whatever I just did is not correct. I'm looking at on whole interval on the picture, minus 3 and 3. But that's not what they're asking me. They're asking me to shrink the domain to minus 1 and 2. So I'm going to take a highlighter and I'm going to highlight from minus 1 to 2. This is where we're looking at. So I'm going to put brackets. And I need to only look at this. Actually, I will not do it in blue. I need only look at, let me make it fat and show you, from this point, oh, that's too fat. From this point to here. Does that make sense? That's why restriction domain matters. That's why you have to keep in mind what domain is. Domain is minus 1 to 2. Since the function is continuous, and since it's located on the closed interval, there is absolute max and absolute min, which give us green light to start looking at it. Don't look at things that do not exist. That's kind of makes sense. Let's not spend time on that. But in this case, it exists. From the graph, you can try to guess what it is, and we're not gonna guess. We're actually going to calculate it. Especially if you have lots of hills, you don't want to keep guessing. Heartbeat has so many max and mins, and all of them should be found using derivatives, not by guessing. And that's all important. Talking blah, blah, blah is amazing. Let's actually just do the problem so you know how to do it on the homework and the test solution. So my steps say 1A, find critical points. Critical points, critical numbers, critical value, whatever the book says. CNs. I call them CNs, CVs. Find the critical points. Last time we covered the definition. That's going to be the most important definition for Montes for you. And in calculus 3 again. Critical points are coming from derivative when derivative is 0 or does not exist. This case is specifically important. Over here, derivative does not exist because it's a cusp, and we still need to check that point. And visually, I can see it's probably going to be local minimum. But is it global, though? I don't know. So critical points means, let me copy the function because I don't want to keep looking up. You don't have to copy it again. Oh, actually, let me distribute it. It's highly recommended to distribute before you differentiate. I finished grading exams, and your grade's going to show up right now. I just scanned them all, send it to not right now, don't take your phone. It all depends on Mac's classes. So I sent everything to him, so I put those grades in, and last time he was very fast. So last time he finished by the end of my class, but I don't know if he has exams today. Many people do product rule when you don't have to do product rule, so maybe don't do product rule, you know. Many people decided to perform product rule like this. And it was correct, I did not take points off, but it was so much longer. If you distribute, you just use power rule, simple as that. Same it was with the quotient rule. Many people decide to perform something x1/2, x cubed, and they decide to perform quotient rule. If you know how to simplify that, then power rule is much easier. So let's not do product rule everywhere. Kind of, it's your choice, but it's too complicated. Let's find derivative. When I distribute it, now I can find derivative. 2 times 2/3 x 2/3 minus 3/3 is minus 1/3, right? Good. Minus 5/3 x to the 5/3 minus 3/3, it's 2/3. Put it in the box. That is highly recommended. We're going to have first derivative and second derivative, and you will need to use both. So whatever you put in the box will be important. Visually, it's just so much better to locate it fast. What we're doing right now, we want to find where this is 0 and where this is D and E. Those are going to give me potential critical points. So we're going to do that. D and E, I don't see points D and E here. That's weird. So to make it easier, I highly recommend, it's not required, but I highly recommend to create a fraction. Create one single fraction. It will save lots of efforts in the future. I just noticed how many mistakes were eliminated when students started creating the fraction after my suggestion. So derivative will be common denominator. I see, so let me tell you, x to the minus 1/3. So that's the one that's gonna go down to the denominator. Then I also see 3 in the denominator, so let me put 3 here. Then left hand side, 2 and 2 give me 4 minus 5. This whole guy is here. That is going to be x to the 2/3, but we're creating common denominator, so it's going to be multiplied by x to the minus 1/3. 1/3 minus, right? X to the, so blah, blah, blah. I think minus. x to the 1/3. Let's just check. If you are confused, which probably you are, let me just factor out things that I can see I can factor out. I can factor out 1/3, and I can factor out x with a smaller exponent. Always factor x with the smallest exponent. It makes sense. X squared minus x cubed. Which one you factor? X squared. Open parentheses. It's going to be 4 minus 5/3 x to the 2/3. Yeah, I told you it's going to be minus. Minus, because when you factor, you subtract the power 1/3. So it becomes plus. Oh, I'm correct. It's good.
And 5/3 is 5.
5/3. Thank you. Good catch. So that's going to be multiply. Should I divide? How to explain it better? I guess multiply by minus x to the 1. Yes, because we put it in denominator, blah, blah, blah. I think this way it's easier to understand. So I factored it out. Factor. I don't want to spend too much time on algebra, but from grading exams yesterday and the day before yesterday, I realized many people are very bad at algebra, which is not the shaming part. It's just the fact. Like, it's just, algebra is hard, and it gets worse somehow in calculus 3. Again, people can take triple integrals and differentiate 7 times, but then forgot what is 5 over 17 times 17 over 5 is. And that is okay. But you kind of lose points on the test because of it. So yeah, let's try to pay attention with parentheses and algebra. You need to keep practicing to get better at this. The derivative becomes very beautiful. 3x to the 1/3 in the denominator, 4 minus 5x. Much better than before, because 2/3 plus 1/3 is 3/3. So it becomes x to 1. Now I have a fraction. I want to see where it is 0 and doesn't exist. But the zeros are coming from the numerator, and D and E are coming from denominator. Make sense? So those are D and E points. Interestingly, in this class, we don't cover this terminology, but actually, the good points, the 0 points, are called stationary points, and the bad points, the D and E points, are called singular points. And that's what you heard this phrase, singularity. Singularity means bad, some kind of destruction, dysfunction of the criteria. Singularity means something is breaking, and that makes sense. So this terminology is used in this case too. So the top gives us a very specific, simple answer, 4/5. That's from the numerator. The bottom equals to 0 gives us also a very simple answer. Do you know what it is? 3 times x to the power gives you 0, which means x is 0. Exactly. I heard you saying that. Those are your possible critical points, or critical numbers, or critical values. But before I declare that, just like last time, you need to have an extra step. I call it 1b. Check that they are. By the definition, the critical points, so check, cannot be called critical points if they are not in a domain. Check the domain. And kick out the extras. Domain was chosen as -1 to 2. Are they in a domain? 4/3 seems to be less than 2, but positive. So x equals 4/5. This point is correct. X equals 0 was also included. Both are okay. That's a very informal way to say it. They are both in a domain, right? Both, I guess, let me see. In the domain. So we can call them now critical points, critical values, critical numbers. Actually, it's supposed to be called critical numbers. So don't move after this. Let me slow down. Do not include 1b. Do not include critical numbers outside of the domain. These are extras. That's my way of explaining it. These are extras. Don't include extras. As always, check out those graphs. You might have a critical point. So you might have lots of different hikes. So this is a hike. You have lots of hills and lots of pits. If they ask you to find min and max, derivative will show you all of these, all of them. And then you tell me, yeah, but I don't know, I don't need all of them. I only need the one I hiked. That means you choose to restrict domain. Thus, you need to kick out the extras. Math gives you all the options. You as a scientist decide which one are extras. So you have to kick out those that are not in a domain and only work with those needed. Sine and cosine have infinitely many max and mins. But from minus pi to 7 pi, you will have only a specific number of them, and so on. So you have to be good at this. You have to be careful with the domain. The next step is the most fun one. You list everything you have. List all the important stuff. List. Make a list. That's how I tell people on the exam when they stuck with a problem. I like, this is when you make a list. And they're like, yeah, I remember how to do that. So it's a very good hint somehow. Make a list. In my notes it says, list critical points. Let's do points, I guess. And points. What are end points? Do you know? Can you guess? It's just from English.
Minus 1 and 2.
End points are the end points of the closed interval domain. A and B, or x sub 0 and x1 and x2, whatever you want to call them. You make this list. The list now has 4 points, 4/5 and 0. Those came from critical points search. And then x equals minus 1 and x equals 2. Those are A and B. Here's your list. Make a list. This is my way of organizing the information. You don't have to do the idea. You have to plug it all in the original function. But I like to put this in a closed interval like so. But how you organize it, that's your choice. I like it this way. Step 3, let me see. So make a list to A and to B. Evaluate original function at all of those points you just listed, critical points and end points. So we're gonna do it using this list. Step 2, A and B. It's convenient to rewrite the original function again, especially since you might not remember what the heck was it. Plug in, let's do that. Plug into the original f of x. And the original f of x was x to the 2/3 times 2 minus x. Here you go. Or you can do the not factored form. You choose. This one is easier though. So before we start doing that, I just tell you the idea. We have potential hills and pits of the hike. They're asking me to find the biggest one and the smallest one. But I just need to check the height then. I'm going to plug everything to the original, choose the biggest one and choose the smallest one. That's the answer. So that's the student's favorite problem on the test. Everyone do really well on these. So I'm just boringly take my calculator and plug every point. 0 is the easy one. 0 gives you 0. Minus 1 is not too bad. And then the other, and 2 is very good. When I plug 2, what it gives me? What does it give me? 0. So I just need to calculate the other 2. 4/5. I like the exact answers. 4/5 to the 2/3 times 2 minus 4/5. You simplify and you have like a nice answer. The thing is, when you have exact answer, you don't know if it's bigger or smaller than other answers. So for this case, engineers are very happy and physics major. Finally, we actually need to approximate it. Because I want to know, is this number bigger than 3 or 2 or 1? What is that number? Minus 1. This is your algebra here. Do you know how to calculate minus 1 to 2/3? 2/3 means, yes? Cube root, that's because of 1/3. And then 2 means -1 squared. So actually, I will show it just because I can see that people are struggling with algebra. Which is, again, it's not bad if you know that you have a problem and you're working on it. You have to reflect on it, admit you have a problem with algebra, and practice it through. That's very important. Times 2 plus 1, because minus gives you plus. And the answer is 3. I have 4 answers. Choose the biggest output and the smallest output. The biggest output gives you global maximum at that input, and the smallest output gives you the global minimum at that input. What is the global maximum here? What's the biggest number as an output? 3. Thus, I'm going to put it in a box. F at -1 gave me 3. That is called global maximum. Global maximum. And I can start answering. Answer. This problem is longer to explain than you actually do it. So that's why it's very good for testing. Answer. -1, 3 is global max. This notation means at x equals -1, we have located global maximum, the biggest mountain, top of the mountain. And how high it is? It is 3 units high. So say 3,000 feet or whatever. So that's what it means. Where? -1, that is say 1 unit to the west, if you think about it. And how high it is? 3 units high. And then let's find global minimum. What is global minimum? It's not a tricky question. You can tell me. 0. Is it possible to have several global minimums? Yes, why not? Sine and cosine have infinitely many. And they're all the same. -1 and 1, sine and cosine. Remember? They have infinitely many global maximum and global minimum. It's possible for a mountain to have 2 the same height tips of the mountains or pits. So I'm gonna put this in orange. At 0 and at 2, the function ends up to have global minimum. So let's put a bullet point, or like 1 and 2. At 0, 0 and 2, 0, we have global minimum. And from the picture you saw that. Let me show you again. So again, I guess let's not put x and y with equal sign. At location 0 and 2, we have global minimums, and the heights are 0. Here it is, so you can see it on the picture. The function hit 0 twice, like a ball jumping from the floor. The ball fell to the floor, hit its minimum height, jumped up and hit the floor again. And we can see that from the graph. So we have 2 minimums and 1 global maximum. Where the global maximum end up to be? Did I ever mark it? No. Where is the global maximum now? At -1. So let me copy here and show you. Whatever I showed you before. Oh, I already have it here. Check it out. How amazing. This is the graph we're looking at, because we're not looking at the whole thing. We have to look at the graph on the restricted domain. No domain expansion. I still cannot let it go. This joke is so good. So the global max is happening where? At -1. How high it is? 3. The global mean happens at 0 and 2. How high the global mean is? 0 height. 0 units height. Can you do this on a test? Like literally, if I give it to you next week, which is not the case. This is doable. So usually the students love problems like this. What do you think? Yes?
With the... Oh, no.
Good. You answered your own question. That's the best. Good job. Let's do one more when I will trick you with numbers of critical points and critical numbers. X cubed minus 3x squared plus 1. Classical problem. Polynomial is keep wiggling. I mentioned my office hours. If polynomial have a cubic shape, it wiggles 3 times. So it changed direction 3 times. Up, 1, 2, 3. Up, down, up. Or down, up, down. If it has 4 power, then it changed direction 4 times. Up, down, down. That's why it's even. Or down, up, down, up. 5, 1, 2, 3, 4, 5, and so on. So it's fun to find all those hills and pits by taking the derivative. The only important thing is, where is it? If I don't have any restriction from minus infinity to infinity, there is no global max, no global min, because the function is forever, this cubic function is forever increasing on the right and decreasing on the left. When we restrict the domain, it changes the situation. Let's mark it. I use a highlighter, but whatever you want. From 1 to 4 over here. And then I can take another color and highlight it again. We're only looking at the graph over here. You see, the graph in 2D gives a shadow from -1 to 4. So we choose kind of the shadow first, and then from the shadow we see what part of the graph we should look on. The shadow officially called projection, and we're going to learn this in Calculus 3. The shadow can be 2D, like in this case, and 3D, like in our case. A 3-dimensional object has a 2-dimensional shadow with the area. And guess what? A 4-dimensional object has a 3-dimensional shadow projection, and we're going to learn that too in Calculus 3. So all of this is still a domain. My shadow is domain of my body, and I am a domain of a 4-dimensional Ukrainian instructor with a third eye and, everything. So here it is, from 1 to 4. Can I ask you a question? Like, yes. If the function was x to the 4, blah, 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 it would look like this. Up, down, up, down. And I don't have any restriction on domain. Does it have absolute minimum? So it goes like this. No. Does it have absolute maximum? Yes. So that's interesting. Even functions, they have absolute value on infinity. Remember parabola? It has absolute minimum or absolute maximum. Depends if it's concave up or concave down. Depends on that A. If A is positive, it's smiling. If A is negative, it's sad. So that means you will have questions in your homework and on your exam when we give you function on the open domain and it has a global max or min. And we're going to teach you how to prove that later. Okay. Again, after blah blabbing, let's just do it. Do you have comments on this or questions? Ideas? No? TikTok? Who's watching TikTok? Let's do it. Step 1A. If they ask you to find, did I ever mention what we're looking for? Find global extrema. That's the short way to say it, extrema. That means global min, global max. You will see all this terminology. It all means the same thing. The moment you see find global, local, min, max, you know what to do. You take derivative, and then you think later. So before thinking, you take the derivative. That's how I recommend to start. 1A, take a derivative. It is, what do you have? 3x squared minus 6x. Amazing. Beautiful. And now you have to find zeros and D and E's. Can you double check? Do we have D and E's? Good job.
No,
How come?
because there's no denominator.
No denominator. There's no square root that can be negative inside of the square root. Polynomials are continuous everywhere. Polynomials are just very good functions. The one we had before actually also was continuous. So they're very good. There's none. No D and E points. That's why this example is a little bit too simple for the test, to be honest. But you will see it in your homework and in general. Let's solve for the 0. That's algebra for you. So 1b, you need to find, is it 1b or not? Let me be consistent. 1a, solve it. Yeah, 1b is get rid of the extras. So 1a, solve it. 3x squared minus 6x equals to 0. How do we solve that? Not distribute, the other way. Factor. Yeah. X minus 2 equals to 0. Don't put it on each side. Some of you will do this mistake, and I will show you why this is wrong. This is correct. I'm fine with that. Then you divide by 3x, and it's going to be x equals 2. And you're like, I found it, because I can divide by 3x. And you give me this answer, and it is wrong. The panda is crying somewhere in China. Pandas are not happy when you mess up the quadratic equations, okay? Why this is wrong? You cannot divide by 0, remember? And that is the reason why you cannot divide by x. What if it's 0? So when you do that, you're actually losing a solution. So you have to write down, oh, we also divided by x, which might be 0. So you have to include it. In general, do not do that. That's how students lose points, lose solutions in general. So I highly recommend to see it as product that gives you 0. Then x is 0. And x is 2. What makes this product 0? 0 and 2. Here you go, have two solutions. That we have to check if they are in a restricted domain. So it's going to be 1b. Check. Cannot include them yet to the list. We're making a list, but I cannot use them if I don't know that they're good. Domain is, I don't remember. What is domain? 1 to 4 closed brackets. That means it has max and min. Do we have extras? Which one?
0.
X equals 0. We will not include it. But x equals 2. Gonna put it in the box. Put a check mark. Yes, that is a critical point. Oh, let's do critical point. Critical point. Check mark. That's kind of my way of explaining it and my way of notating this. You don't have to do the same thing. But the idea is 1b says get rid of extras. I like to call them extras. Get rid of extras. There are too many hills and hoops and over here. Math gave me everything. Math gave me those two. Here's your max, here's your min. But I don't need the 1 at the 0. For example, it's your business model. And you start from January, month 0. And now it is month 4. That's April, right? I think. But you don't need to include January for some reason. You want to start calculating from February. So your business model will have restricted domain from February to April. What is the profit? That's what we teach in business classes. What is your profit? Differentiate, and they find maximum and minimum of profit function or cost function or revenue function on the chosen domain. So that's why it's important. One of the examples at least. Step 2, make a list. Make a list, plug it in, answer. That's it. The list is x equals 2, do not include 0. It will give you an answer, and you will include it as an answer, and it will be wrong. And then domain, which is 1 and 4. Sometimes I like signing them. What are these? But you don't have to. I don't remember the original function, and I want to write down so it's in my face over there, so I don't make a mistake, plug into the wrong place. Because we will be plugging into derivative later, so it's nice to know where to plug what. I'm plugging into original to find heights. How high is global max? How high is global min? Which is high-low, but it's fine. I'm finding f at 2, f at 1, f at 4. That's why you can see that exam 3 will require a calculator. That will be annoying. 1 is easy. 1 minus 3 plus 1 gives you what? Minus 1. Yes. And the other one you have to calculate. I guess I can write down for you once. 2 cubed minus 3 times 2 squared plus 1. Who is good with algebra calculations? 4 to the 3 minus 3 times 4 squared plus 1. That's me adding your points yesterday before the concert. 100 times 100 exams, and then you're just adding minus 1 plus 3 minus 7 in my mind, and then adding. So that's why you have to keep checking it in case I made a mistake. If I gave you too many points on the exam, you better let me know. And if I took too many points off, you also should let me know. So that's just a human mistake. When we use Gradescope, if you know what it is, that is a magical thing because it adds points for me. But when I do it myself, cannot guarantee it's correct. It's like correct up to the error. Say like 3%. So it has an error. What did you say about f of 2? minus 3, good one. And f at 4? 17. Find the biggest, answered. Find the smallest, answered. The biggest one is obviously 17 at 4. That is, by obviously I would say like you visually can see it, but also math. Global max. And then do you see the smallest one? Negative 3 happens at 2. Yeah, be careful with that. Global mean. And you answer and you move on with your life. Answer. The answer is at 2, comma, minus 3. Sometimes they ask you to order it, mean and max, and for the web work. We have global mean. That means at 2, location 2, the global minimum is 3 units below x-axis. So 3 units low. Yeah, that's the way to say it. At 4, it's 17. That is global max. That means at 4, there's the highest tip of the mountain. How high it is? 17 units high. So the maximum profit, for example, was $17,000 at the month April. But when we started the business in February, we were losing money because you need to advertise and so on. So there's lots of applications, of course. What do you think about that? I'm telling you, this is like the best chapter ever. 4.1 is amazing. That's why it's due Monday. You can do it. It's very nice looking chapter. Any questions about that? Because we can move on to 4.2 after this. Questions, suggestions, ideas? Yes?
Local extrema different from this?
We're going to do this right now after this. Local extrema has to be tested. Global is easier. You just check the max and means. Everyone can do it, right? To be honest, you can teach a person who knows numbers, like a third grader. 17 is bigger than minus 3 and minus 1. Well, they probably need to know what minus means. And they said yes. But then local one, you have to test it using derivatives and first derivative test or second derivative test. But it's a good question. That's why it's a very different idea here. And in calculus 3, it will be amazing. We're going to have 3D objects. So imagine here's the pit, but what if it's 3D? Here's the mountain, but what if it's 3D? In 3D, we will have maximum, minimum, and you will have to approach it from all directions, x, y, and z direction. So it's going to be depth will be involved. And then we will have a third option. There is an option when it's not just max and not just min. And that's the coolest part of it. That's called saddle point. Here's, if you imagine a chip or a saddle, here's a saddle. You're sitting on a horse. That's what the saddle is, right? Over here. This thing, let me make it better. This thing is minimum over here. That's why you're sitting in a saddle where there's a minimum. So what's the question you can ask? It is a minimum. But when you look at from perspective from the front to back, over here, it becomes maximum. So it depends on the perspective of third-dimensional object. If you look at the butt of the horse, the person definitely is at the minimum of the back of the horse. If you look at the side of the horse, then you are the maximum of its legs. That's why you're on the horse, not below the horse. That is amazing. So in 3D, we're going to have saddle point, and that will be also checked and tested by a derivative test. Still actually first derivative test and second derivative test too.